Hello, my name is Luke Johnson. I'm the Subsurface Director for Oilfield Production Consultants. And today we're talking about a method that OPC uses to deliver approximate accuracy for its clients when it comes to history matching complex fields. It's an experiment-led approach that we call simulation sprints. We, as a consultancy, are often tasked with history matching complex assets. Clients come to us and say, we need you to help us match the production data to the asset so that we can understand more about our field. The challenge is how much time and money will that take to achieve it. A history match process in its entirety may start all the way back at petrophysics, taking the measured logs and core and deriving logs that are helping us understand porosity, permeability, and saturation. We may need to redo the geophysics. Perhaps the last history match didn't quite explain the connectivity between certain wells that could be down to structural compartments. Equally, maybe that happens to be associated with some of the sedimentology. Maybe we need to dive back into the geology and help better characterize what's going on. But either way, by the time we get to the stage of building a static model and ultimately simulating it, the challenge with a traditional workflow is it's a very long distance away from providing that economic answer that the client is really needing to make their next business decision. This traditional way of doing simulation history matches is what we call a waterfall project design, and it can cost you in three very important manners. It encourages each discipline to deliver technical excellence, regardless of whether that excellence is impacting the business decision. It also means that those disciplines, as they go through their silos, are not able to learn from each other, and they tend to hand a best guess onwards. But a lot of the interpretive work that we do within the oil field is not necessarily completely deterministic. We have a degree of freedom in a lot of the interpretation steps that rely upon expert judgment. And unfortunately, that sequential approach often causes a time compression towards the end, particularly when you get down to simulation. And so in truth, a lot of history matched models have actually been achieved by applying large multipliers to the continuous properties or building in artificial regions to try to manage the way that fluids are moving. None of that is geological. An alternative approach that can be explored is the ensemble. With today's compute power, all of those uncertainties that people can explore, in theory, could be built into a range of different possible answers. And using complex workflows, we can branch all of those different uncertainties together to build a plethora of possible simulation models. And in theory, by analyzing those simulation results against the actual production data, we should be able to determine which series of branches achieve the correct answer. And if we've correctly characterized the asset and captured all of the possible answers of the subsurface, this should be true. But unfortunately, due to the significant degree of uncertainty and the limited amount of data we have in the subsurface, it's not often a matter of characterizing each of the branches in the tree. Sometimes it turns out that the actual answer is something we hadn't thought of at all. And so at OPC, we reframe the entire approach. We don't think of modeling as the deliverable. We think of modeling as a tool. We like to think of ourselves as scientists running a series of experiments to hone our understanding and make use of all possible information in informing every one of those uncertainties and decisions that we make during our interpretation steps. That means that when someone comes to us with a task to history match a field, we stop and we change it and ask the missing question: why do you want us to history match the field? What's the objective that you are seeking? What is the fundamental business decision that you are trying to address with these assets? And particularly, it's important that we have that clear understanding so that we can do it efficiently, but also focus on what matters. because confidently wrong is a disastrous outcome in the subsurface. If we anchor on particular interpretations, we end up with a precise and repeatable representation that can cluster around an outcome that isn't the truth. If we instead reframe it to experiment with the system and understand the complexity of how all of the different kinds of data interact with each other, we can quickly and accurately hone in on what the truth is. Less precise, certainly, but approximately accurate is a position where you can make a confident business decision. In a mature field, that might be a question about a field redevelopment plan, or perhaps you are in the middle of an infill drilling campaign trying to optimize the next series of wells. You might be looking at assessing an enhanced oil recovery parameter that you might want to look at changing from a water flood to a gas injection. These will all have different impacts on what you want to try to address. So let's take an example, a real-world example that we worked on for infill drilling. To protect client anonymity, what I'll do here is I'll represent the field with this simple four-way anticline, and we can throw onto that the wells that have been producing in this asset. So a mature field, a field with, say, 20 years of production history. Now, we don't have to throw high science immediately at that. We don't have to get in and build the most complex model. In fact, oftentimes we can get a long way by stopping and thinking a little. And to do that, in this case, we started off by looking at the production that each of the wells had. And we could represent that with an effective drainage radius because, well, we know that the next production wells are not going to want to twin areas that have been effectively swept by others. We also know the structure is relatively finite. So we're going to target the areas that are not within those existing areas of production. And in fact, in the particular asset we're talking about through here, we could only really identify 20 viable candidate bottom hole locations in the field. The client also told us that they needed 6 new wells drilled. In essence, 6 other production wells had failed, and they wanted to replace those. Now, in a mature asset with production and a production facility above it, really every one of these wells is likely to be economic. So the question that we help them reframe is not to achieve a history match for this field to justify a precise estimate of the net present value and IRR of each of the individual well locations. Instead, we reframed it to say, we want to help you identify what are the best 6 out of these possible locations. And so simply, instead of thinking it in that complex interaction of all of the field, we can now start to think of it as a order of possible locations. We take those 20 wells, in this case numbered A to T, and what we're going to do is try a series of experiments to understand what are the best 6. It was a complex opportunity because the asset itself was underexploited in a particularly structurally complex area, a slump complex on the side of the field. For obvious reasons, they had avoided drilling this in previous campaigns. There are a couple of wells that had penetrated the slump, but the reason why they'd walked away from exploiting that too heavily was that the plumbing of it was obviously very chaotic. They had some wells that appeared to be connected to injectors at great distance, where adjacent wells that should have been seeing pressure support were showing complete isolation in the production. However, this was the area where we had opportunity, so we needed to answer that question. We needed to design an experiment that would allow us to try to understand where the best 6 were. And what we told the client is that we are going to give you the first answer at the end of day 1. To put it in context, the previous history match had taken them 2 years to achieve. The way we start is by simplifying the problem. Okay, we're in a slump complex. We don't really need to pay attention to the rest of the field. What we want to do is understand the plumbing inside the slump. So focusing in, we can build sectors around that and generate some reasonable geological representations of the slump complex. It wasn't perfectly matched to seismic. In fact, the seismic hadn't really identified all of the faults. What we needed to do was essentially solve a very complex 3-dimensional puzzle with a lot of well penetrations, very well correlated stratigraphy, and a lot of rotation within the blocks. But nonetheless, we set ourselves a requirement that we would build a simple model within a day, we would simulate it, and we would rank every one of the answers from 1 to 20 to determine what were the best that we could generate from this particular representation. And so at the end of the day, we had a new order of best to worst wells. Now, this wasn't a great answer. We would look at it the next morning and realize, well, there are plenty of things that have got issues with it. And what we want to do now is resolve that as best we can. But we're also not going to give ourselves an infinite amount of time. We set ourselves 2 days to solve the next problem. So the challenge was, what were we going to give ourselves 2 days to do? Now, in this particular case, we essentially had a very simple petrophysical model. So we decided in the next couple of days, we were going to do a Fashi's distribution. That would allow us to control some of the relative permeabilities within the different layers, as well as try to get some more complexity associated with stratigraphic compartmentalization. That gave us a new order to the series of wells. But the next time we looked at it, we thought there seems to be a few more contacts inside here. So we start adding additional compartments. We weren't happy with the faults, so we continued to modify those. And we continued on a time basis to run additional experiments, one after the other. And at the end of each of the simulations, we were ranking those wells to determine from 1 to 20 what were the best 6 locations to target. What was particularly interesting out of this is after a series of these sprints, in fact, only 4 weeks into the process, what happened is that the order of the wells stopped changing. As we progressively improved our characterization of the field, the top 6 remained the top 6. And we changed the experiments then, not to continually improve our understanding, but to try to dispute that hypothesis. So we try to create the counterfactual. What do we do now, given our new characterization, a new level of understanding? What are we going to do to change that answer? After only a couple of months, we had solved what we were satisfied with to understand which were the locations to drill. And this was very important to the client. They had a rig coming in 6 months' time, and they needed to give that recommendation. The challenge that we had was explaining to everyone how we were focused on honing in on that approximate answer, not by approaching it from a point of precision, not by trying to build a Goliath of a model where we have every possible piece of it built in entirety. We instead were focusing in on trying to resolve the core business question. What makes it work is that we start each of our sprints with a new hypothesis to test. We look at the last set of results, we look at what we understand, and we start with the biggest gap. And we design a tool-agnostic experiment that's going to test or try to resolve that uncertainty within the time frame that we have given ourselves. The great benefit of that is that we would have times where we wanted to try to match a water breakthrough from one well to another, identified in the production, talking to the simulation engineer, that we might have to try to solve by reframing the structural framework with the geophysicist, or perhaps by changing the petrophysical heterogeneity to try to achieve a greater degree of bypass. What was happening is that all pieces of insight, from production data to geophysics to petrophysics, were all feeding in a continuous loop here of honing our understanding. That's why we were converging towards a position where the decision began to stabilize, because for the first time, we were truly using all of the information in this asset to help understand what was the best possible way of describing the field. The key to making this work, though, is discipline. It's important to engage with decision makers at the beginning of the project to recognize that we're not here to give you a precisely wrong answer. The traditional approach of this waterfall sequence of events has caused you to be in this position where you've got a challenge right now. A time-bound business decision is coming. The wells are going to be started drilling in 6 months, and we were under the pressure to give the best possible recommendations. And so scoping that very carefully and explaining what we were going to do allowed the decision makers to buy into the process. Equally, by following through a series of sprints, the decision makers also have access to clear documentation throughout the journey. They can read at the end of each sprint what was the hypothesis that we were testing, what was the experiment that we were going to do to test the hypothesis, and what were the results of that outcome. And then at the end of each sprint, we're interpreting what's the gap in our knowledge and what are we going to do next to try to resolve that. That clear documentation gives the decision makers confidence that the uncertainty is resolving. It also allows them to see where to stop the study. This keeps the costs at the absolute minimum. Those explicit stop criteria are not then a hypothetical perfection of a history match, but instead when the decision has stabilized. And that allows you to communicate in the right terms. It's not about a precision over a history match. It's about a level of confidence and a risk tolerance that we all agree upon for the next decision to be made. If this is something that you think you might need to have a look at, please reach out to us at OPC. We've been deploying this globally and influencing everything from exploration decisions all the way through to those mature field development activities. The simulation sprint approach is an honest way of getting you to a business recommendation quickly and effectively.